Hello friends, this is lecture number 7, complex analysis, and our topic of discussion today, Cauchy Riemann conditions in polar form. And these are the conditions. We're going to prove these conditions. Okay. And you can follow me on Insta, and my Insta ID is Oja Lekhajit 123. Okay, so today is the 31st December, and this is the last video of 2023. Okay, so I hope that I will be able to upload lecture 8 on 1st January on 2024. Okay, so now let's start. And before we start, please subscribe the channel, hit the bell icon so that you get notified when new video will be uploaded, and share with your friends. Help me to grow my channel, inspire me to create new contents for you. And if you like my videos, please hit the thumbs up button. Okay, so stay connected. Now let's start. So now, Cauchy Riemann conditions in polar form. So this is our topic of discussion today. So now, let us suppose, let me write the conditions first. These are the conditions, okay, in polar form. We can write this way. So let me prove this. So let us suppose that f of z, this is a function of complex variable, so which can be written as u plus iv, where u and v both are functions of x and y. Okay, functions of x and y. Okay, here you see u and v are functions of x and y. It doesn't mean that u is function of x only, v is function of y only, not like that. So u is also function of x and y, and v is also function of x and y, right? So hope you have understood this. So now you see, let me tell you that z is equal to z is a complex number. Z is equal to x plus I y. Okay, so let me take that way. So here in polar form, it can be written in this form. So we have already discussed in here you see, I don't know which one, lecture 1 or 2. Previous lectures are given in the description box. Links of those previous lectures given in the description box. We have already discussed about the polar form of a complex number, maybe in the first or second lecture, so you may go through. Okay, and if you need lectures on Laplace transformation, those are also available in my channel. You may check the playlist. If you search Laplace transformation, then you can find it, or I'm going to provide the link in the description box, link of the playlist of the Laplace transformation. Okay, so now here you see, so according to Euler's formula, we have already discussed that this polar form can be written in this way, right? R into e to the power I theta. Okay, so this can be written as e to the power I theta. We have already discussed this, okay, by Euler's formula, right? So now you see, here r is the mod of z, which can be obtained by root over x square plus y square. Just hope you have understood this. So this is the value of r, that is mod of z, that means mod of the complex number. So here you see, let me take this one as equation number 1. Now from equation 1, here you see u plus iv, that means f of z. Instead of z, we can write r into e to the power I theta, because here you see we have got z is equal to this. So if we use this value of z here, then we're gonna get this, and it's gonna be equal to let me take this one as equation number 2. This is equation number 2. Now let us differentiate equation number 2 with respect to r partially. Okay, if we differentiate equation number 2 partially with respect to r, okay, then what we're gonna have, del u by del r plus complex this I, imaginary number I, del v by del r. Then if you differentiate the function f of z or f of r into e to the power I theta, then you're gonna have f dash r into I theta, and as you can see, this is function of function. this is itself a function. Again, it is function of another function, that is r into I theta. That's why we have to differentiate the function inside the bracket again. And if we do so, then what we're going to have, then we're going to have this. If you differentiate r into e to the power I theta with respect to r, then derivative of r is 1. Then we're going to take e to the power I theta as constant in that case if we differentiate partially. So hope you have understood this. So now you can see here, you can see, let me take this as equation number 3. Okay, now here you see again, if we differentiate it, okay, differentiating equation number 2 with respect to theta, okay, then we're going to differentiate it again partially. Then we're going to have this result, okay, del u by del theta plus I del v by del theta is equal to f dash r into e to the power I theta. So here you see we have differentiated this equation number 2 with respect to theta again partially. So then again, function of function, again if you differentiate it again with respect to theta, then this time we're going to take r as a constant, okay, e to the power I theta is the function, differentiable function. Then we're going to get here I r e to the power I theta, right? So here you see, this is suppose equation number 4, this is equation number 3, suppose. Okay, let me take this one as equation number 3. Okay, this one as equation number 3 and this one 4. Now if we use 3 here in 4, so if you see, this is f dash r dot e theta, e to the power I theta, and into e to the power I theta, that is nothing but this one, right hand side of the equation number 3, right? If you take this one into e to the power I theta, which is the right hand side of equation number 3, so then you can replace it by this, right? So that means using 3 in 4, you can see, because f dash r e to the power I theta into e to the power I theta is equal to this, and here we have got e to the power I theta into f dash of this, which is the right hand side of this one. If you see, if you take this one, if you write this one outside somewhere, then this one and this one represents this, and which is equal to this, right? That's why you can replace this one by this and into this, right? So hope you have understood this. Now let me write as it was. Okay, so what we're gonna do here, we're gonna use equation number 3 using 3 in 4. We get this. So here, this one into this one, it is replaced by the left hand side of equation number 3. Then into we have IR. So IR, that's what we have got. So here, let me write here IR. Okay, so if we multiply this, if we open the bracket, then we're going to get this result. So here I into I, that's going to be minus 1. So that's what we have got, right? So now if we compare the imaginary part with imaginary part of both sides and real part with the real part of both sides, let me go to the next slide. Okay, so let me write the last step again here. Okay, so comparing the real and imaginary part. Okay, this is the imaginary part, here is this is imaginary part. If you compare these two, and imaginary with imaginary, then real part with the real part. Okay, this one and this one, these two are real parts, and then equating the real and imaginary parts, okay, of both sides, we're gonna have this result, this one and this one, right? Okay, so here you can see these two can be simplified as this one, del u by del r is equal to 1 by del v by del theta, right? And on the other side, this equation can be simplified as del v by del r minus 1 by r del u by del theta. So these are the Cauchy Riemann conditions in polar form. Right? So hope you have understood this. So in the next video we're gonna solve exercise problem. Just wait. Problems from the mathematical physics books by H.K. Das. Okay, H.K. Das. Okay, I am going to give you the solutions of exercise problems from the book of book by H.K. Das, mathematical physics books. That's a very good book. Okay, so now you see, I hope that I can upload that video tomorrow on the 1st January. Okay, so wish you a happy new year. So thank you for watching this video. Stay connected, and please do subscribe the channel and share with your friends. Okay, bye bye.